Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we are going to introduce the second tool, iteration. So in this topic, we will describe iteration. We will see how it can be used to solve algebraic problems. We will then describe the fixed point theorem and look at a number of examples. We will then discuss issues with iteration and the fixed point theorem with respect to, for example, the maximum number of iterations and the tolerances we are willing to accept in our approximations to such solutions. The next tool we will use is iteration. Now, for iteration, first we require a mathematical function f, which may represent a numerical algorithm. The function f takes a value in a space and maps it to another point in that space. Second, we require an initial value or initial approximation, and we'll usually call it x naught or v naught or some other initial value. Now, an iteration occurs when we start applying the function to x naught. So, calculating f at x naught, we get a result. We will assign this result to a new value called x1. So rather than saying equals, I'm using an arrow to emphasize that we are assigning to x1 the result of applying f to our initial approximation or initial value. Having done so, we can now apply f to this value x1, and having done so, we will assign the result to x2. Having done so, we can now evaluate x2 at f and assign the result to x3. If we repeat this arbitrarily often, this is going to produce a sequence of as many values as we either want or require. Now, of course, the significance of any such sequence depends both on f and the initial value. Now, the function f may be a simple arithmetic function. On the other hand, it can also be a very complex algorithm involving a number of steps, especially if, for example, we are describing a function f mapping vectors onto vectors. However, here we're going to start with a very simple function. Here, f at x is simply defined as mapping x onto x squared. Even here, depending on the initial value, the behavior will change. We're going to look at three initial values, 0.1, 1, and 2. If we start with 0.1, squaring that we get 0.01, squaring that we get 0.0001, and so on and so forth. And as we can see, this seems to converge to the value 0. On the other hand, if we start with the initial value 1, squaring 1 always leaves you with the value 1, and so this creates an infinite sequence of 1s. However, if we start off with 2, squaring that gives you 4, squaring 4 gives you 16, squaring 16 gives you 256, and so on and so forth. And as you can see, this appears to diverge to infinity. We've already seen one example of iteration. We already saw that if x approximates the square root of 2, then 2 over x is on the other side of the square root of 2. So if x is less than the square root of 2, 2 over x is greater than the square root of 2, and vice versa. Consequently, the average of these two should be a better approximation of the square root of 2. So the function we are going to define is f takes x and maps it to the average of x and 2 over x, giving the formula x over 2 plus 1 over x. Now, if our initial approximation to the square root of 2 is x naught equaling 1.4, well, 1.4 has a 1% relative error in approximating the square root of 2. Well, applying this function f, we already seem to have a better approximation, 1.14. And if we now apply f to x1 to give us x2, we get an even better approximation. In fact, after only 3 iterations, we have all 16 significant digits correct. And if we apply f to x3, the result is unchanged. So it seems that if we are using double precision floating point numbers, this has converged to a single value after only 3 iterations. Now here's an exercise for you. Come up with a similar formula, but now for approximating the square root of n for a given positive real number n. This introduces our first theorem, the fixed point theorem. This theorem says that given the equation x equals f at x, where f is a function, and given an initial value x naught, then if the iteration of f starting with x naught converges, then it must converge to a solution of the equation x equals f at x. Now it's important to note here, normally the function f will be a real valued function of a real variable, and therefore x naught will be a real number. However, it can also be a vector valued function of a vector variable, say a 5-dimensional vector being mapped to a 5-dimensional vector. In this case, of course, the initial value must also be a vector. Now let's look at the problem we just looked at. Here we see a plot of both y equals x and a plot of y equals x over 2 plus 1 over x. You will note that the value square root of 2 appears to be the point where x equals f at x. Consequently, if we start with an initial value and we start iterating, it should converge to that point. Now, what is that point? Well, x equaling x over 2 plus 1 over x, we can subtract x over 2 from both sides, and now let's cross multiply both sides by x, multiply both sides by 2, and we get that this is true if and only if x squared is equal to 2. In other words, yes, the point at which this function f at x equals x is when x equals plus or minus the square root of 2. Now we could write a function to do this for us. Here the function fixed point has as its first parameter a function f that takes a double as an argument and returns a double. The second parameter will be the initial guess or the initial point. Now, inside this function, we have an infinite loop. Now, with fixed point iteration, we could have an arbitrary number of values that we calculate. However, we really only need the current value and the previous value. So what we're going to do is we're simply going to use the parameter x naught as our local variable. we will store the current value of x naught in the local variable previous x naught. We will then assign to x naught the iteration of x naught. So we'll calculate f at x naught and assign that result to x naught. We will then check if x naught is equal to the previous value of x naught, that means it hasn't changed. We will then assume that we have converged and return the value of x naught. We can now author a function called square root 2. Now this takes a double as a parameter and then returns x divided by 2 plus 1 over x. This is the function that we will iterate. We can now author a program. First, we will modify the cout object by having its precision set to 16. So now it will cout will print floating point numbers to 16 significant digits. We can then call fixed point with square root of 2 as a first argument and 1.4 as a second argument. If you were to run this program, it would then print out 16 significant digits approximating the square root of 2. All right, we can also author this in MATLAB. So here we have a function in MATLAB where the fixed point function has two parameters and it has one return value x naught. We have an infinite loop. That infinite loop starts with while true and the end of the loop is at the statement end. As you can see, the end of the function is also at the end of the corresponding end keyword. Now, inside the infinite loop, we set previous x naught is equal to the current value of x naught. We then update x naught by assigning it the function f evaluated at x naught. We then check if x naught is equal to the previous value of x naught, we return. What do we return? Well, we return whatever value x naught currently has. Because after all, if you look at the declaration of the function, what is returned is the value of x naught. You could use, as we do here, a parameter, but you could also give it another value like y or fp. Now, this must be saved to a file called fixedpoint.m. The way MATLAB finds a function is to look for a file with the function name .m. All right, let's now run MATLAB. Format long, so we have 16 significant digits printed. Now here's something cool that you can do in MATLAB. You can define simple arithmetic functions with an assignment statement. So square root of 2 is being defined as a function. It has a single parameter x, and the value of the function is x divided by 2 plus 1 divided by x. This is a very nice feature to use when you're modeling. We can now call fixed point with the function handle square root of 2 and 1.4 as the second argument. And we get as our answer the square root of 2 to 16 significant digits. Now, at the start of this topic, we looked at iterating the function f at x is defined as x squared. Now the fixed point theorem says that if an iteration of this function converges, then it must converge to a solution of x equals f at x. There are two solutions, when x is equal to 1 and when x is equal to 0. Now note that if the initial x value, x0, lies somewhere on the open interval from -1 to 1, then if you try it out, you'll see that the iteration actually converges to 0. So yes, it does converge to a solution to x equals, in this case, x squared. If x0 is equal to 1 or it is equal to -1, then the iteration converges trivially to 1. Otherwise, the iteration diverges. So if you start off with x0 equaling -1.1 and start squaring that, that sequence will diverge to infinity. Now, a sequence may not diverge to infinity. A sequence may alternate between two different points, but it simply does not converge. This leads to our first problem that we must deal with. When do we stop iterating? Well, we're going to have to parameterize our algorithm for them to stop iterating after a fixed number of iterations. We must also check to see if the current iteration is no longer finite. After all, it may be diverging to infinity very quickly. We can now modify our fixed point function to take a third argument, max iterations. So now, instead of having an infinite loop, we will have a loop that iterates a maximum of max iteration times. Now, what do we do if it doesn't converge? If we throw an exception, then we have to set up the try-catch mechanism to catch that exception. Otherwise, of course, the program terminates. Instead, we're going to return not a number to indicate that the fixed point iteration did not converge. Then the user calling this function simply has to check the result to see whether or not convergence occurred. So from before, we iterate. However, what happens if x0 becomes infinity or not a number? Well, inside the C math library, there is an isFinite function. It returns true if x0 is a finite floating point number. That is, it is not infinity and it is not a number. Well, if it is not finite, then it's diverged. So we will return not a number. We could also author these changes in MATLAB, adding one more parameter, max iterations. Now we have a for loop. That for loop has a loop variable iterations, and it takes on the values 1 through max iterations, whatever that is. Now, one interesting point. Everything in MATLAB is a floating point number. So max iterations will likely be a floating point number. Consequently, this will interpret max iterations as an integer. Now, if it does not converge, we have to explicitly assign x0 the value not a number, and then we can return. However, inside the loop, we do as before, And now we are going to check. If x0 is not finite, then we set x0 is equal to not a number and return. Now, interestingly enough here, the not operation in MATLAB is the tilde. You'll recall that this is the bitwise complement operator in C++, which is essentially the bitwise not operation. So it's not the exclamation mark, it is the tilde in MATLAB that represents not. Then, when we launch MATLAB, format long, now we are defining this function inline g as taking a single argument x and returning x squared. If we now call fixed point with g and an initial value of 1.4 with 1,000 iterations, we find that it does not converge, and therefore the result is not a number. Suppose instead we start with a function f at x being defined as cos of x. Now this has a single solution close to x is equal to 0.7391. Interestingly enough, for this particular function, it doesn't matter what value of x0 you start with. This iteration will converge to this one unique solution. Let's take a look at this. However, before we do, you may have already noticed this. Although if your calculator is in degrees, you may get a different answer. In secondary school, you may have been bored from time to time, and on your calculator, you just start with a number and then proceed by simply pressing down cos over and over and over again. You were essentially iterating the cosine function, and you may have noticed that it actually does converge. You may also maybe tried this with a sine function. What happened then? Do you remember? All right, let's iterate the cosine function, and let's start with x is equal to 0.7. Well, after 20 iterations, the first 3 digits seem to have converged, but that's about it. After another 20 iterations, it seems that we seem to have 7 significant digits, maybe 8. So it's a much slower convergence than we had with the approximation of the square root function, where it converged in only 4 steps. So this leads to our first question. When do we stop iterating? Well, when we had the square root of 2, we iterated 4 times, and after 4 iterations, there was no change. Here, we've iterated 40 times, and there's still going to be some time before it converges. So, iterating cosine takes a longer time than, say, for example, the x over 2 plus 1 over x example. But with iteration, we really don't normally need 16 significant digits. In fact, as engineers, we seldom require more than 6 significant digits. And so therefore, we don't want to wait forever, and we don't want to unnecessarily waste computing power. Therefore, we're going to make an assumption. We are going to assume that if 2 successive approximations are close enough, that is, less than some step tolerance, then we are going to assume that our most recent iteration should also be close enough to whatever it's converging to. Now, unfortunately, this is not necessarily true, and mathematicians can always come up with a function for which this fails. But for most engineering cases, this is sufficient. Now, this parameter that we're passing, the step tolerance, is an absolute tolerance and not a relative tolerance. For example, we don't even know if the solution is non-zero. So if the solution is actually at 0 or very close to 0, the relative tolerance may not even be defined. However, you as an engineer should be aware of what you are expecting the solution to be when you use such techniques. So you should know the maximum absolute error you are willing to accept. We can now update our C++ function. We're going to include a parameter, the step tolerance. And this might be a value like 10 to the negative 6. We're making it the third parameter and not the fourth because this actually concerns the convergence of a successful run of this function. Max iterations is a parameter that dictates when this function has failed. So let's put the more important one first. Now, if the absolute value of the difference between x0 and the previous x0 is less than this step tolerance, we're going to return x0. We could also update this in MATLAB, adding a step tolerance parameter and then returning if the difference between our current approximation and our previous approximation is less than this tolerance. All right, so in MATLAB, we can use format long. We will now call fixed point. Now, previously we assigned a function to a variable, and so we can just pass that. However, cosine is just an identifier. There happens to be a file called cos.m, which is called when you call cosine with an argument. But you now have to tell MATLAB that you really mean to interpret cos as a function saved in a file called cos.m. So to do this, you indicate that it is a function handle by prefixing the identifier with the @ symbol. So, calling fixed point on the cosine function with an initial value of 0.7 and an absolute tolerance of 10 to the negative 6, allowing for up to 1,000 iterations, we get this approximation. When we compare this to the closest actual solution correct to 16 digits, we do see that the absolute error is less than what we dictated. All right, so in this case, it appears to have worked as expected. Following this topic, you now understand how iteration can be used to solve analytic problems. You've been exposed to the fixed point theorem. You understand that we must limit the number of iterations. After all, the iteration may actually diverge, or it may take a long time to converge, too long that we're willing to wait. And we must also set the absolute tolerance for what we are willing to accept for our solution. You have seen the implementations in both C++ and in MATLAB. Here are the references, the acknowledgements, the colophon, and a disclaimer. Cheers!